Hi, Assalamualaikum and a very good evening. So today we are from Solid State Physics. We'll be presenting about chemical bonding, which is our title is Covalent Bond. My name is SHAHADAH FITRAH BINTI RAMANI and my group members is Nurul NATASHA, Afika AKASHAH, Siti Nur AMIRA, Nurul ALYAA AZIRA, Inshira ABDULLAH, and Azima AZMI. Okay, next, I will give definition of chemical bonding. First of all, chemical bonding can be defined as the attractive force that hold two or more atoms together in a molecule or an ion. I can say that it is a connection between atoms in a molecule. Chemical bonding also can refer to formation of a chemical bond between two or more atom, molecules, or ion to give rise to chemical compound. These chemical compound are reliant on the strength of the chemical bond between its constituent. The stronger the bonding between the constituent, the more stable the resulting compound will be. Next, the definition of covalent bond. Covalent bond can be defined as a type of chemical bond wherein two or more atoms share one or more electron pairs. And this covalent bond between two atoms is usually formed by sharing an electron pairs between atoms. Next, I will pass the presentation to Natasha.
Okay, I will share about general information about covalent bond. So we have Lewis formulation. In Lewis term, a covalent bond is shared electron pair. The bond between a hydrogen atom and a chlorine atom in hydrogen chloride is formulated as shown. In a Lewis structure of a covalent compound, the shared electron pair between the hydrogen and chlorine ions is represented by a line. The electron pair is called a bonding pair. The three other pairs of electron on the chlorine atom are called lone pairs and play no direct role in holding the two atoms together. So for this Lewis formulation, we have advanced aspect of Lewis structure. First, we have resonance. This is uncertainty is illustrated by the Lewis structure for ozone, which is O3. The following are two possible structures. In these cases, the actual Lewis structure is regarded as a blend of this contribution and is written in that structure. So this blending together of this structure is actually a quantum mechanical phenomenon called resonance. At this stage, resonance can be regarded as a blending process that spread double bond character evenly over the atom that participate in it. So next we have hypervalence. In Lewis term, hypervalence requires the expansion of the octet to 10, 12, and even in some cases, we have 16 electrons. Hypervalence compounds are very common and in general are no less stable than compounds that conform to the octet rule. So that's all for general information about covalent bond.
Okay, next we have characteristic of covalent bond. So we have three characteristics of covalent bond, which is bond length, electronegativity, and bond polarity. Next, bond polarity and molecular polarity. Okay, so for bond length, other covalent bonds also have non-bond length, which are dependent on both the identities of the atom in the bond and whether the bond are single, double, or triple bonds. So as we look here, table 4.5.1 is the list the approximate bond length for some single covalent bond. So the exact bond length may vary depending on the identity of the molecule, but will be close to the value given in the table. Okay. Next one. Okay. And then for table 4.5.2, okay, it compares the length of single covalent bond with those of double and triple bond between the same atom. So without exception, as the number of covalent bond between two atoms increase, so the bond length will decrease. With more electron between the two nuclei, so the nuclei can get closer together before the internuclear repulsion is strong enough to balance the attraction.
Next characteristic of the covalent bond is electronegativity and bond polarity. So although we define covalent bonding as electron sharing, the electron in the covalent bond are not always shared equally by two bonded atoms unless the bond connects two atoms at the same element. So in the diagram, in hydrogen, there will always be one atom that attracts with the electron in the bond more strongly compared to the others, such as HCl, hydrochloric. So a covalent bond that has an equal sharing of electron is called non-polar covalent bond, as in the diagram A. Meanwhile, in the diagram for part B is called polar covalent bond, where the covalent bond has an equal sharing of electron. Next. So the distribution of electron density in a polar bond is uneven. It is greater around the atom that attracts the electron more than the other. For example, the electrons in the HCl bond of hydrogen chloride molecule spend more time near the chlorine atom than near the hydrogen atom. So note that the shaded area around the chloride in figure 2b is much more larger than it is around hydrogen. So this imbalance in electron density will result to a build-up of partial negative charge designated as a negative delta on one side of bond, and a partial positive charge designated as a delta plus, delta positive on the other side of the bond hydrogen. So as you can see in figure 3a, the separation of charge in polar covalent bond result in an electric dipole two-pole represented by the arrow in figure 3b. So the direction of the arrow is pointed towards the delta negative end, while the positive tail of the arrow indicates the delta positive at the end of the bond. Next. So any covalent bond between atoms of different elements in a polar bond, but the degree of polarity varies widely. So some bond between different elements are only minimally polarity, with electron being transferred rather than being shared. So to judge the relative polarity of a covalent bonds, the chemists will use electronegativity so that they could measure of how strongly of an atom attracts the electron when it forms a covalent bond. So there are various number of scale for rating the electronegativity. So in the diagram that's shown is Pauline's scale. So to read Pauline's scale, the values derived follow predictable periodic trends with higher electronegativities toward the upper right of the periodic table. So over here you can see that fluorine has the higher value, the highest value. Next.
Okay, next, bond polarity and molecular polarity. So there is only one bond in the molecule, which is the bond polarity determines the molecular polarity. So any diatomic molecule in which the two atoms are the same element must be a non-polar molecule. So a diatomic molecule that consists of a polar covalent bond, such as HF, is a polar molecule. So actually, a polar molecule is a molecule in which one end of the molecule is slightly positive, while the other end is slightly negative. Okay, so the two electrically charged regions on either end of the molecule are called poles, similar to a magnet having a north and south pole. So when we place between oppositely charged plates, polar molecule orient themselves so that their positive ends are close to negative plate and their negative ends are closer to the positive plate. Okay, next. Okay, as we look at this diagram, the polar molecules are randomly oriented in the absence of an applied electric field. So in an electric field, the molecules orient themselves to maximize the interaction between opposite charge. Okay. Okay. Next, for molecule with more than 2 atoms, the molecular geometry must also be taken into account when determining if the molecule is polar or non-polar. So the diagram is a comparison between carbon dioxide and water. So actually, carbon dioxide is a linear molecule. So the oxygen atoms are more electronegative than the carbon atom. So there are two individual dipoles pointing outward from the C atom to each O atom. So actually, for example, the boiling point of water, which is 100 degrees Celsius, is high for such a small molecule due to the fact that polar molecules attract each other strongly. That's all. Next.
Okay, so I will explain next slide. So I will explain for the properties of covalent bond. Next. Here I will discuss on 4 properties of covalent bond, which is the boiling and melting points, the electrical conductivity, the bond strength, and the bond length. Next. For the first properties of covalent bond, which is boiling and melting point. So covalent bond has a low boiling and melting point due to the weak intermolecular forces. So as discussed before, in covalent compounds, all molecules are bound weakly to neighboring molecules. Therefore, it takes very little energy to separate covalent molecules from one another. Thus, it makes the melting and boiling point of this bond is low. The second one is the electrical conductivity. Covalent compounds does not conduct electricity, which makes it a good insulator, as covalent bonds do not have charged particles or ions that are capable of transporting electrons to neighboring molecules. The third, which is the last one, is bond strength and bond length. As discussed before, when more electrons are shared, the bond will become stronger, so the shorter the bond length.
For the last part, we will be presenting about the application of covalent bonds. The first application of covalent bond is from sunscreen. One of the ingredients that I will be explaining has a covalent bond as one of its main ingredients. Sunscreen lotions contain titanium dioxide, TiO2. Not only that, it is for a fact that titanium dioxide is a crystalline solid that is insoluble in water and liquid, but soluble in concentrated acids such as sulfuric acid, hydrochloric acid, and nitric acid. It has characteristics or also known as being odorless and absorbent. By absorbent, for example, can be absorbed into human skin. Next, titanium dioxide is a covalent compound in which the titanium atom is bonded to each oxygen through double bonds. It consists of covalent bonds with titanium in a +4 oxidation state. So from here, why is titanium dioxide in sunscreen? Titanium dioxide is usually used as a pigment for painting, as a coloring in the food industry, especially in sunscreens and cosmetics. So that would be my overall structure of my presentation. So let's move on to our next presenter.
So the next application of covalent bond is nail polish remover. Nail polish remover contains acetone, which is CH3-2O. The characteristic of acetone is colorless ketone and organic solvent that is both volatile and flammable. Acetone is water soluble and miscible in ethanol, ether, benzene, ethanol, and ethanol. So acetone is in the carbonyl group, which is a polar covalent bond of oxygen and carbon. As we know, the electronegativity of carbon is 2.55 and the electronegativity of oxygen is 3.44. So acetone is naturally produced in plants and by the human body as a breakdown product of body fat. In trees and SHAHADAH, tak nampak. Tapi in trees,
Sorry.
Okay, it's okay. So why acetone must be included in nail polish remover? Because it's a powerful degreaser used to clean objects made of metal and glass. So that's all from us. So these are list of differences.
Okay. That's all from us. Thank you.